Alireza, and thanks to the organizers for inviting me to give a talk in your seminar. So I hope you can hear me well. My title today is Mutation of Tau Exceptional Sequences, and this is a project which I've been working on for quite a long time. So the main results I will talk about today are quite new. They are from this preprint here from February this year, but some of the background for this course is in these 4 papers mentioned above. Some of them are joint with Bethany Marsh, some with Eric Hansen, but the new preprint is joint with both Eric and Bethany. The aim is to generalize the theory of exceptional sequences for hereditary algebras to general finite-dimensional algebra using tau tilting theory. So our work builds a lot on, of course, the seminal paper by Adachi Yama-Reiten, where they introduced tau tilting theory, which is now 10 years since it appeared in a journal. And it builds also very heavily on the 2 papers I mentioned below, the one by Gustavo Hasso, reduction of tau tilting theory and torsion pairs, and lattice theory of torsion classes beyond tau tilting theory by Demonet, Iyama, Redding, Reiten, and Thomas. It appeared last year, but on arXiv in 2017. So, okay. So the plan will be to first tell you a little bit about the theory that we are aiming to generalize, namely exceptional sequences for hereditary algebras, which was studied by first by Crowley-Boy and Ringel in 93-94, so 30 years ago. And then I will say some, and especially about mutation of such sequences. And then I will say something about tau exceptional sequences. And at last, try and motivate and state some recent results about mutation of such tau exceptional sequences. So this is the plan. Let us start out very easily or elementary somehow by looking at hereditary finite-dimensional algebras over a field, which we just for simplicity today assume is algebraically closed. So that means we can assume that up to Morita equivalence or algebra is the path algebra of an acyclic quiver. And so this is lambda is our algebra, Q is our acyclic quiver, K is our algebraically closed field. So we're looking at path algebras, and then we're looking at finite dimensional modules over such algebras. Okay, we want to do define things recursively. So we need to start with the most basic case, namely take a quiver, which is just one vertex and no arrows. So then we have a simple algebra, which is just isomorphic to the field itself. And there is only one in the composable modules, which is again just isomorphic as to the regular module, lambda regarded as a module over itself. So this is the basic case. Then the second example is, so the second most simple example is to look at A2. So the quiver given by 2 vertices, 1 and 2, and 1 arrow from 1 to 2. You take the path algebra of this gives you 3-dimensional algebra, which happens to be isomorphic to the lower triangular matrix algebra over K. Now the module category is just slightly more complicated. There are 3 in the composable modules. I call them S2 and S1. That are the simple ones corresponding to vertex 1 and 2. And then there is the projective one corresponding to vertex 1, which is just an extension of S2 and S1. And S2 is also projective, so it could also call it P2. And this displays the exact sequence starting with P2, ending in S1. But if we add some dot here, we can also think about this as the AR quiver of this module category. All modules over this algebra are just direct sums of copies of these three modules. Okay, so these are very simple algebras and module categories. But we want to, in principle, we want to understand module categories for any quiver, also later path, or for any path algebra over any quiver, and we want to later also include path algebra's modulo relations. But for now, there are no relations. But it can get arbitrarily complicated if the quiver is slightly more complicated than the ones we looked at so far. So one possible way to attack that is to look at smaller module categories sitting inside our module category. And that is somehow one way to motivate the theory of exceptional sequences is to think about exceptional sequences as given flags of module categories sitting inside or ambient module category. So let me try to be a bit more precise. So, but let us still, now from the start, just consider this very small examples. But so what do we want? So one way to think about this is to look at smaller module categories sitting inside our module category. One way to think about that is to look at algebras sorry, subcategories which are sort of close in size to mod lambda, but still smaller. So co-rank 1 module categories sitting inside mod lambda. Well, we can think about that as full subcategories of mod lambda, which are equivalent to a finite dimensional algebra of co-rank 1. So this notation means that the number of simples for lambda prime is the number of simples of lambda minus 1, so co-rank 1 module categories. And we want them to sit inside mod lambda in a nice way. And nice here should mean that X is a wide subcategory, so it's closed under co-kernels, kernels, and extensions. So sort of the exact structure of X is the same as the one for mod lambda itself. So this is, so what we're looking for are wide subcategories of co-rank 1 inside mod lambda. Okay, let us see what that would look like in our toy example. So for A2, we can find 3 co-rank 1 subcategories. Each of them are generated by one indecomposable module. So S1, P1, and P2, each of them, if you just take the additive closure of one of them, they will generate a wide subcategory, which is just equivalent to mod lambda prime from example 0. So here in this example, there are 3 co-rank 1 subcategories. Of course, when things get complicated, we don't want to first find the whole module category and then look at how to construct sort of from below wide subcategories. We rather want to find a general way to identify wide subcategories. So one thing we can note, or what we can note in this example, is that, well, this S1 we can actually write as the hom perp of P2. So if you take P2 and look at all modules which have no maps from P2, this is exactly the additive closure of S1. Similarly, P2 is just the hom perp of P1. How about the third wide subcategory, the additive closure of P1? Well, it's not the hom perp of any of the modules, but if you write this subcategory, where we take all modules such that there are no homs from S1, and also no x1 from S1 to X, then we get exactly the additive closure of P1. And this is called the Geiger-Lensing perpendicular, the Geiger-Lensing perpendicular category of S1. And now this doesn't look completely uniform, but we see that if so P1 and P2 also have no extensions with anything since they are projective, so we might as well write 0, 1 here. So what we see is that if we take each of these three modules and take the Geiger-Lensing perpendicular, then we actually get all three wide subcategories of corank 1. Okay, so this is not a coincidence. So actually there's a theorem by Schofield and Geiger-Lensing saying that in the hereditary case, if you're looking for a wide subcategory of corank 1, well, then this is exactly, they are exactly given by these perpendicular categories given by x1 and home vanishing of a module for indecomposable module. So if you take an indecomposable indecomposable and exceptional module. So modules which, in addition to being indecomposable, satisfies this, that x1 EE is equal to 0. So in the example we looked at, the three modules all satisfies this. None of the three have self-extensions, so we can take the Geiger-Lensing perpendicular. This gives us exactly the wide subcategories. Now, in the hereditary case, we can also note it's not hard to show that, well, these categories you get in this way, if the module category you start with is hereditary, these perpendicular categories are also hereditary. That means they are equivalent to a module category of an hereditary algebra. Okay, so this gives us one way to define exceptional sequences. It's not the original way it was defined, but it is not so hard to see that it is equivalent to the usual or original definition. So an exceptional sequence in this, an exceptional sequence is now a sequence of indecomposable modules, which are all, where the last one, En, is exceptional and such that the remaining part of the sequence is an exceptional sequence in the Geiger-Lensing perpendicular category of En. And remember, this perpendicular category is a module category again, so it makes sense to talk about exceptional, and it's a hereditary, it's equivalent to the module category hereditary algebra. So this recursive definition makes sense in the hereditary case. Okay, so it's easy to see that such sequences cannot have length longer than the number of simple modules or vertices if it's a quiver algebra of lambda. And we call it complete if the length is actually equal to the number of simples. So mostly today we will consider complete exceptional sequences. So notion makes sense more general for n smaller or equal to the rank of the algebra. Okay. So this is exceptional sequences. And one thing to note, which is important if we want to check that this is equivalent to the original definition, is that, well, since this Geiger-Lensing perpendicular categories, since they are wide, especially they are closed under extension, it means that if you pick a module which lies inside such category, and now we identify such category with mod lambda prime, where lambda prime is a hereditary algebra, then it's easy to see that a module is exceptional as a lambda module if and only if it is exceptional as a lambda prime module. So this one needs in order to verify that this is equivalent to the original definition. And I also include this because when we now want to generalize in a little while to tau exceptional sequences, this property is unfortunately lost, which makes our theory a bit more complicated than in the hereditary case. Okay. Now let us discuss mutation still for hereditary algebras, and let us go back to our toy example, A2. So in this case, since we found so there are 3 exceptional modules and 3 corresponding rank 1 wide subcategories, this gives us 3 exceptional sequences. So these sequences will be, so we have P1 is an indecomposable exceptional module. And then we want some module in the Geigel lensing perpendicular. Well, that will have to be P2. So that's our first exceptional sequence. And then we do the same reasoning for the 2 other exceptional modules. Then we get, let me see. Then we get P2, S1. And we get S1, P1. So these are the 3 exceptional sequences. And now what we look at, if you stare on this for a few seconds, we see that, well, there seems to be some kind of system. We see that if you move this P2 over here and move this S1 over here, and then move this P1 over here, this seems to give some way to produce an exceptional sequence from its neighbor somehow, the way we've written it. And this is exactly what mutation does. So there's 2 ways to think about it, So this is left mutation, and there's a corresponding right mutation. And of course, what you want is to be able to produce new exceptional sequences from some kind of starting point by doing some operation on these exceptional sequences. So one first thing to note, first fact is that, well, actually, when we go from BC to C star B, meaning that means we move the first one to the right, and then we have to replace C by something. Then first fact is that, well, C star is uniquely defined by B in the sense that in the rank 2 case, we are here in the rank 2 case, then C star B is the only exceptional sequence of the form X, B. More generally, if you had higher rank, then an exceptional sequence is uniquely defined by n-1 of the n object that it constitutes. So what I said now is true for, sorry, I should be more precise. It's true for complete exceptional sequences, not for any exceptional sequences, but for complete. And here, since we are in rank 2, a complete exceptional sequence has 2 objects. Also, I will not write down the explicit formulas for how to compute C star, but there are explicit formulas in terms of B and C. We will look at some formulas later, which generalize this formula, so I will not write them down here. They are sort of given by approximation theory. Okay. So this has several nice properties, and actually one of the main results, or maybe the main result of Crowley-Boy and Ringel, so Crowley-Boy showed this for the algebraically closed case, Ringel for more general, is that this operation that we indicate here, it gives a transitive braid group action on the set of complete exceptional sequences. So maybe I should say a little bit more. If we have n equal to 3, there will be 2 possible places to mutate. We can either mutate with respect to the first pair, or we can mutate with respect to the second pair, and then this will satisfy braid group relations. And then, yes, as I said, this will then give a group action, which is transitive. Okay, so that was what I planned to say about the hereditary case, which we now want to try to generalize. Are there any questions at this point before we move on to the case of tau exceptional sequences and arbitrary finite dimensional algebras? If not, then I will proceed now to talk about general finite dimensional algebras. Let's start out by an example. So this is, just a second. Can you still hear me? I think I... Yes, okay. Yeah, okay. Good. So now let's still look at an algebra of rank 2, but now let's take this path algebra modulo a relation. So we have a quiver with 2 vertices, cyclic as 2 cycle, and then we mod out the ideal generated by one of the compositions. So then we get, this is an example of a so-called Nakayama algebra. There are 5 indecomposable modules, which I here have drawn in an AR quiver. So there are the simple modules, there are 2 modules of length 2, and there's a module of length 3. And this one is identified by this one. And this 1, 2, and 2, 1, 2 are the projective modules, while this and this in my notation are the injective modules for this algebra. Okay. Now, if we try to use the Geiger-Lensing theory for this, it will fail in the sense that, for example, if we take the simple module 1, and take the Geiger-Lensing perpendicular category, it will not longer be wide. This one, the Geiger-Lensing perpendicular of 1 will consist of the 2 projective modules, and they don't constitute a wide subcategory. Also, we can note that, well, actually, this category, the additive closure of 1, 2, is wide, but we cannot find it as Geiger-Lensing perpendicular subcategory for any tau exceptional or for any module Y. So we cannot directly use Geiger-Lensing perpendicular categories in order to identify, say, co-rank 1 wide subcategories any longer in this case. So what do we do? Well, we revert from exceptional modules to tau-rigid modules. So motivated by Adachi Yama-Rayton's tau tilting theory, we, instead of looking at modules with the property that x1 mm vanishes, we want to look at we want to have a stricter property, namely we want x1 m with any module which is generated by m to vanish. So gen m here means all modules x such that which are factor objects of modules in add m. So you can take copies of m and have an epimorphism to x. That's exactly the when x is in gen m. So we want to replace this property of x1mm vanishing with the property that x1m gen m is 0. And so this is then what's pointed out by Adachi Yama-Rayton is that, well, this is the same as saying that there are no maps from hom m to tau m, where tau is the Auslander-Rayton translate. So if you used to Auslander-Rayton theory, Auslander-Rayton translate, this is maybe the easiest way to think about such modules with this property. But if you're more used with homological algebra and not so much with the AR theory and finite dimensional algebras, you can just think about modules with this property, which is then clearly a stronger property than just x1 mm vanishing. Okay, so this is ID number 1. ID number 2 comes from Hassel's paper where he looked at reduction techniques or reduction for tau tilting theory. So then for an tau-rigid module, so a module with the property above, you should not look at the Geiger-Lensing perpendicular like we did in the hereditary case, but we should rather look at the tau perpendicular category J of m, J for Hassel, which is given as follows. So you take the modules x such that there are no maps from m to x and also no extensions from m to gen x. If we just wrote x here, then we would have the Geiger-Lensing perpendicular. But now we want more strict. We actually want x1m to gen x to vanish. And then this is actually equivalent to taking the intersection of m perp intersected with perp of tau m, using the same kind of properties as for this equivalence. It's easy to show that we have that these are the same. So with this definition, then Hasso proved that, well, if you take such a tau perpendicular category of a tau rigid module, I should here specify that M is tau rigid for this theorem, then the Hasso proved that then this J of M is actually equivalent to the module category of a new finite dimensional algebra. And if M is indecomposable, then this algebra has rank 1 smaller than the algebra you start with. And then in the paper I mentioned by Demonet, Iyama, Reading, Rayton, and Thomas, they prove actually that this is a wide subcategory of mod lambda. So this was what we were looking for in the hereditary case when looking at the Geiger-Lensing perpendicular, co-rank 1 wide subcategories. And tau-rigid modules gives us such categories. But we should note, let me see, second. We should note that this theorem is not quite as strong as the one given by Schofield and Geiger-Lensing in the hereditary case. It only says that this tau rigidity gives a sufficient way to find wide subcategories. There will actually, in general, for general algebras, be co-rank 1 wide subcategories which are not given by such construction. Okay. But with this definition, there is a very natural way to define tau exceptional sequences. Now, after having seen this theorem of Hasso and Demonet, Iyama, Reading, Rayton, and Thomas, it's natural to define a tau exceptional sequence as follows. So we take a sequence of indecomposable modules, and now just to stress that, and now this is for general finite dimensional algebra lambda, and just let's just assume that we now just talk about complete tau exceptional sequences. This could be done for any n which is smaller or equal to the rank of lambda, but let us just do it when we have n, just to ease notation, for sequences of length n, where n is the rank of the algebra. So a sequence of length n of indecomposable lambda modules is a complete tau exceptional sequence if the last one, En, is tau rigid in mod lambda, and the remaining sequence is a tau exceptional sequence in the tau perpendicular category of En, which, as was stated on the last slide, is equivalent to mod lambda prime for some algebra of co-rank 1. So it makes sense to talk about tau exceptional sequences in this wide subcategory. But now it's important to note that it's very different from the hereditary case, because the EIs which appear here for I smaller than n, they are not necessarily tau rigid as objects in mod lambda. So for example, En minus 1 have to be tau rigid in J of En, but it's not necessarily tau rigid in mod lambda. So this is different from the hereditary case, where being exceptional in the module category, the ambient big module category you start with, is the same as being exceptional in these Geiger-Lensing perpendicular categories that we consider. So this is also one thing which complicates our theory or generalization to general finite dimensional algebras. Okay, so this is the definition of tau exceptional sequences. Now let's try to find them, or find some in our small example. So here it means we need to identify all indecomposable tau rigid modules for this algebra, or example algebra. There were 5 indecomposables altogether, but we note that this 2, 1, this is not tau rigid. You can see that by using both of the definitions. I mean, we can first note that there is an extension starting with 2, which is generated by 2, 1, and ending in 2, 1. So that means that x1 m comma gen m is non-zero when m is 2, 1. So this is not a tau rigid module. We can also note that, well, actually tau of 2, 1 is 1, 2. That's why I drew it this way. This is the AR quiver. So there is a map from m equals to 2 equal to 1 to tau of m, because there's a map from 2, 1 to 1, 2. So this is not a tau rigid module, but the 4 other indecomposable modules are tau rigid. So we can take the tau perpendicular for each of these 4, and that will give us the 4 co-rank 1 wide subcategories, namely the additive closure of 1 coming from tau perpendicular of 2, 1, 2, the tau perpendicular O2 is the additive closure of 2,1. And the additive closure of 1,2 is J of 1, and J of 1,2 is the additive closure of 2. Note now that 2,1, it was not tau rigid in the module category, but in this subcategory, it will be tau rigid because it will actually be projective, right? Because this subcategory here is again just equivalent to mod K, to simple algebra. So therefore, this will be a projective and hence tau rigid module in that subcategory. So this gives an example, something which is not tau rigid in mod lambda, but is tau rigid in a tau perpendicular subcategory. Okay. So now, if we use the definition that I wrote down for tau exceptional sequences, here we can see the 4 tau exceptional sequences, which are induced by finding the 4 tau rigid modules in the composable tau rigid modules and completing them to tau exceptional sequences. So these are the 4 tau exceptional sequences for our example algebra. And if we stare at this for a second, we might get optimistic and see that this looks quite similar to in the hereditary case. We can start by moving this. We can move this 1 over to the right. We can move this 1, 2 over to the right. We can move this 2 here over to the right. But then something happens. This 2, 1, if we try to move that to the right, we don't get back here. I mean, the 2, 1 has to be replaced by 2, 1, 2, which is natural because 2, 1 is not tau rigid, so it cannot appear to the right in any tau exceptional sequences. Because as the rightmost object must be a tau rigid object, so we need to replace this 2, 1 with something which is tau rigid. That's the philosophy. While for the other ones, we see that, well, when we move the 1, 2, and the 2 to the right, well, these are tau rigid modules, and it works nicely sort of to flip them over to the right. So this is what we want to try to do now. And we want to try to define a mutation operation on the tau exceptional sequences for this case and for general finite dimensional algebras, and especially to explain what happens here when we have to change from 2, 1 to 2, 1, 2. So we want to give now explicit mutation formulas which explain how to do these operations here. And we want to do that in such a way that we generalize what is going on in the hereditary case. Okay, so the rest of the talk will be about how to do this. So we need quite a lot of technical sort of ingredients. So we'll try to focus on the ideas here. It gets quite complicated to work out all details, but I will try to explain the main idea. Okay, so first let me tell you something about this Hasso reduction when we go from an algebra to from a module category to the tau perpendicular module category. Says something what happens then, and this will give an indication of how to get from this 2, 1 to this 2, 1, 2. Okay, so whenever you have a tau rigid module M, this gives you a torsion pair. So this is actually due to Ostlander's Smala, so a classical result, which was very much used in the Adachi-Yama-Reiten paper, where they defined and studied tau tilting theory. So tau rigid module, so defined either by this or by X1M Gen M vanishing, gives us a torsion pair. Especially when you have a torsion pair, it means that you can take a canonical sequence for any module. So for any module X, there is an exact sequence with a factor of X living in M perp, which is the torsion-free class in this torsion pair, and the kernel, the submodule in Gen M. And this construction is very nice. There is a unique such sequence with these properties that the first object is in Gen M and the last one in M perp. And the construction is also functorial. So this is very nice. And as a almost immediate consequence of that this construction, we get a nice bijection. So this was, yeah, in the way I stated here, it is from joint work with Bethany Marsh, but it's just a small adaptation of what was proved by in the paper by Gustavo Hasso, which I'm referring to. So this FM gives a bijection between those indecomposable modules in mod lambda. So this means indecomposable lambda modules, such that which are sort of compatible with M as tau rigid modules. So that means that X plus M is tau rigid, but you want in addition X not to be generated by M. So if you apply FM to any of this, you will get a tau rigid module in the tau perpendicular category. And this will give a one-to-one correspondence on the level of indecomposable objects. Okay, so this is very nice, but it's not quite enough for us. We need something slightly stronger or a bit stronger. We want also to sort of understand what happens with those modules which are generated by M. So for this, it helps to, instead of just looking at the module category, we look at what Adachi-Yama-Reiten calls tau rigid pairs. So a tau rigid pair is a pair MP, where M is a tau rigid module, as it was above, and then P is a projective module with no maps to M. So hom PM is 0. And so if you have such a tau rigid module and a projective P which do not map to M, then we call this a tau rigid pair. We use, just for simplicity, we use this notation. We call such a pair, or use this notation for a pair, M plus P shift, where we think about this shift in the derived category of mod lambda. And we call such objects support tau rigid objects. So whenever we have, so there's a correspondence between tau rigid pairs and support tau rigid objects, which is just given by writing M plus P1 instead of M comma P. So it's just a notation. And then we can strengthen the theorem above and say that, well, if we take an indecomposable support tau rigid object X, no, sorry, if we take a support tau rigid object M, which we call U, then there is a bijection between the indecomposable support tau rigid objects. And here I should have written in dB mod lambda, such that X plus U is support tau rigid. And then we have to mod out with U and the support tau rigid objects in the tau perpendicular category of U. We get such bijection, which extends the bijection in the previous theorem in the sense that, well, if U is equal to M, and we take an object which is not generated by M, then this map EU is just the same as the map FM here in the previous case. So it's an extension of this theorem. But what happens now is that, well, these modules which are generated by M, they are still here, but now they appears as shift of projectives for the tau perpendicular category, or for the module category equivalent to the tau perpendicular category. So that's sort of the bonus with going from this first theorem to the new one, is that we recover the objects which are generated by M, and we will need that for our mutation formula. Okay, so now we're getting close to be able to actually give some formula for mutating. Let us now look at a tau exceptional sequence of length 2, so not necessarily complete anymore. What does it mean? It means that C is a tau rigid indecomposable module, and that B is a tau rigid module in the tau perpendicular of C. That's what we mean by a tau exceptional sequence now. Now, the previous theorem tells us that, well, actually, so that for this we can actually just use Hassel's theorem. This B lives down here, so we can lift it to something up here. Right? So if in our setup C is equal to M and B is some object down here, we can lift that uniquely up to something which is compatible with C. So that means we can uniquely we can replace B, while the lifting of B to some object, some indecomposable object, such that B star plus C is tau rigid. So B star is then the lifting of B with respect to this map. Okay. So for any tau exceptional sequence, we have such a tau rigid module B star plus C. Now, any tau rigid object, and especially B star, has two canonical complements. This is something also again from Adachi-Yama-Reiten, which we can call which is called the Bongard's complement and Cobb-Bongard's complement. What are these? So the Bongard's complement, those are exactly the X projectives in the torsion class perp tau B star. So I haven't talked about this, but this is also a torsion class. So we can take the X projectives in that torsion class. This will give us one complement, Bongard's complement. Then Gen B star, since B star is tau rigid, is also a torsion class. We can take the projectives in that torsion class. That gives us sort of dual thing, namely the Cobb-Bongard's complement. In some sense, this is the smallest. Bongard's complement is in some sense the biggest complement, and Cobb-Bongard's complement the smallest complement of B star, in the sense that they generate the biggest, respectively, the smallest torsion classes containing B star, or containing B star as a projector. Okay. So actually now to define a mutation formula, we need to consider several cases. We need, in fact, to consider 4 cases, and it depends on these cases depends on how. So C is compatible with B star, so it's a candidate. C is a candidate for being a summand in either the Bongard's or the Cobb-Bongard's complement of B star. So these are the cases we need to consider. First, we consider the case where C is projective. Next, the case where C, and I should state, stress that if C is projective, then actually C must be in the Bongard's complement of B star. So then the second case is when C is a summand in the Bongard's complement, but not projective. The third case is when B is a summand in the co-Bongard's complement. And the fourth case is when C is neither a summand in the Bongard's or the co-Bongard's complement. For 3 of these cases, we get quite nice formulas. So we call this the regular mutation. In the fourth case, it's more complicated. And this is the complicated case where C is a summand in the Bongard's complement, but a non-projective summand in the Bongard's complement. Okay. So these are the 4 cases we want when we want to define a mutation formula. So this is what the mutation formula looked like in the 3 regular cases. So first, here is the case where C is not Bongard's, co-Bongard's, and not Bongard's complement. The second is when C is in the co-Bongard's complement. The third is when C is projective. And remember that, so we start with a pair BC. We lift this B to something which is compatible with the C. So this means B star as before plus C is tau rigid. And there's a unique way to do that. So then we replace BC. So we don't, in general, move just B over like we did in the hereditary case, but we replace B with B star. And that will, in general, give us a tau rigid module in the bigger module category. So we start with a B, which is just tau rigid in some tau perpendicular category, but then we lift it to something which is tau rigid in that bigger category corresponding to where we mutate. So these are the formulas. I will not go into details of this. It's just note that these are explicit formulas for how to compute the mutation in these 3 cases. Unfortunately, it's much more complicated in the case where C is a summand in the Bongard's complement, a non-projective summand in the Bongard's complement. So we call that the irregular case. And then in this case, 2 things can happen. Either, so let us see. So we first take the wide subcategory corresponding to B star plus C. This tau rigid module, we take that tau perpendicular category of that, and then we take the smallest torsion class containing that wide subcategory. This is given by closing W under gen. So we take everything which is generated by objects in W and then close under filtrations. This is the smallest torsion class containing W. Then 2 things can happen. Either this is not a functorially finite wide torsion class. And in this case, the mutation is not defined. So we cannot mutate that pair. But if it is functorially finite, then we switch from this B star plus C to some other tau rigid object, which are exactly the non-split projectives in the torsion class. So one can then prove that these are given by, there will be 2 of them, and one of them is not generated by the other. So we say that it's of the form X perp plus Y, where Y is, here it should be not generated by X. Sorry. No, sorry. It's where one is, sorry, I'm wrong. Where y is generated by x. Yes, so this is what we want. And then we define sigma of BC to be exactly xy, where y is this, and x is EY of x prime, where EY is this map which appeared here in this theorem here. But now for the pair x, for this pair, x prime plus y. So that just to give an indication that, well, in this irregular case, it's a more complicated mutation formula. Okay, so this is the explicit formula. So let me now just finish by giving some comments. So first is that, well, this operation on pairs, it extends to operations on sequences in the sense that, well, we can mutate at the last pair, but we can mutate at any consecutive two objects in the sequence. So this gives us sort of operations sigma 1 to sigma n minus 1. One for each of the n minus 1 pairs. But the formulas that was on the last slide, they will need to be computed in some perpendicular category, so not in mod lambda itself. For example, sigma n minus 2, if you want to mutate the pair en minus 2, en minus 1, then we compute this in the top perpendicular of en. So it's only for the last pair that we can use these formulas directly. For the other pairs, we need to compute them inside some top perpendicular category. Okay, so that was quite technical. Let me just at last say some nice things about this. First is that when our algebra is hereditary, or mutation formula actually specializes to the classical mutation formulas. And so then in particular, we do get the transitive braid group action with these formulas for that case. Furthermore, if lambda is either hereditary or tau tilting finite, meaning that lambda has only finitely many tau tilting modules, or the rank is 2, one of these happens, then all pairs are mutable. That means we never get to this situation where sigma of BC is not defined. So this torsion class here will in that case always be functorially finite. So we can mutate any pair and any sequence in this case where lambda is hereditary, tau tilting finite, or rank 2. How about transitivity? Well, if lambda, it's not true in general. So if lambda is 2, then it's transitive if and only if the so-called Hasse-quiver of torsion classes is connected. Since I'm way over time, I don't have time to explain, but this gives us a criteria for connectedness. We don't know what is the case for higher rank. Also, not so nice is that, well, in general, there is no braid group action on the set of all tau exceptional sequences from this formula. This formula does not give that in general. It works in the hereditary case, but not in general. Okay. I think I will end there and just say thanks for the attention.
So thank you very much for your nice talk. Are there any questions or comments?
Sorry. Can you hear me?
Yes.
Yes. Did you say something about the existence of complete tau exceptional sequences?
Yeah. Yeah. Thanks for asking that question. Yes. So there's an echo. Let me try to state it this way. I mean, for any algebra you can find tau exceptional sequences, in the sense that you can just start by picking a projective to the right, and then you can, in the top perpendicular of that category, you can find a projective some module, say M, which is projective in the top perpendicular category of the one you chose. You can put that next, and then you can continue, right? So then you can take a top perpendicular category of this again and continue until you have, and the rank will always go down. So if your algebra has n vertices, the rank is n, then it will always end after n steps, or n minus 1 steps. So there will always be tau exceptional sequences, but it's not true that you can always complete if you something to a tau exceptional sequence, and this is most easily illustrated if you look at let's see, if you look at this example, you see that that 2, 1, 2, the projective in 2, it is tau rigid, but there is no tau exceptional sequence of this form. So this is also different from the hereditary case, where you always can complete. In the non-hereditary case, you cannot always complete, but if you can, then it is a unique complement. Did that answer?
Okay, yes, thank you.
Good question.
Any question or comments? And also, I have a question, Aslak. Is there some condition on algebra such that this mutation be easier? For example, if it works on a path algebra, but for the quiver, acyclic quiver, but with relation, is the mutation is easier or not?
Sorry, the sound in the beginning was a bit bad, so I didn't hear the start of your question. Sorry, can you repeat?
If you work on a tree algebra, that means the path algebra of the acyclic quiver with relation.
If sorry, I'll try to turn up my sound. Or maybe can you type the question in the chat? I'm
yes,
sorry,
yes.
I'm not hear it well.
There is already one question in the chat box, maybe Aslak you can see, by Ramin.
Okay. I don't know why, but I cannot really see the chat. Hmm.
Do you want me to read the question?
I think just a little. I mean, it looks like I have. Just give me one.
Yeah.
Yeah, sorry. Yes, maybe you can do that. Oh, sorry, I'm not able to see it for some reason.
This is a question by Ramin Ebrahimi. He says that thank you for the talk. You said that not all wide subcategories of codimension 1 are tau perpendicular subcategories. Can we study these wide subcategories of codimension 1 using silting modules?
Yeah, okay. Thanks for the question. I don't know the answer. I mean that I know only some examples of such wide subcategories. So there is an explicit example in the paper by Eric Hansen and me, where we just modify an example given in a size paper on semi-bricks. So I don't know the answer to that. Sorry. I could also add that in the tau tilting finite case, there's only finitely many tau rigid in the composite modules. Then in that case, all wide subcategories are tau perpendicular. No, I can't see the chat. No, I found it. Sorry, it seems like I had another Zoom meeting open here. Let me see. There is another question. Was this your question? Let me see. Alireza, if you work on tree algebras, is the mutation of tau exceptional sequence always exist? So what means the tree algebra? What does tree algebra mean?
The path algebra of acyclic quiver.
Oh, right. Let me see. No. So the example in the paper. Let me see. Can you still see my screen? So the example in the paper we have is not is acyclic. So it's given by double Kronecker algebra, and then killing two of the four compositions of length of length 2.
Thank you. So are there any more questions or comments? It seems there is no question. Let's thanks to Aslak again. Thank you for your nice talk.
Thank you.